In this video, we're going to look at an example of how we can use the tails to find lower and upper bounds for a particular p-series. So we're actually going to let's look at the specific p-series 1 over k cubed. And this will be as k goes from 1 to infinity. So this is 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed, and so on. And our first question is going to be to use, let's say, S5 and tails, the idea of tails, to find upper and lower bounds for the actual series itself. Now, the answer to this kind of a problem is going to be based on the stuff in the previous video. The thing that I want to remind ourselves of is that S5 means the series as k goes from 1 to 5 of 1 over k cubed. That would be 1 plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed. And let's see, I do know my cubes, so let's see, that's S5. S5 is going to be 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. And that's a nice finite sum. But the question, of course, is going to be, how far off is this? So what I now want to do is I want to take S5 and bounds for the tail for S5 to create bounds for the entire series. Well, how are we going to do that? Well, we're going to remember that our tails for p-series can be trapped between two intervals. So what I want to remember is that the tail for S5 is going to be trapped between the integral between 5 and infinity of 1 over x cubed dx and the integral between 6 and infinity of 1 over x cubed dx. And this is because R5, the tail of the series, is a right Riemann sum for the bigger integral, and it is a left Riemann sum for the smaller integral. And you can go back to the previous video for the details about why that works. Well, these two improper integrals are both ones that we can figure out in a reasonable amount of time. So let's actually look at what they are. Now, I'm going to be abusing the notation slightly. I'm not always going to be worrying a whole lot about the formal limits, but I'm going to try and do a little bit of the formal limits. I first of all want to start with turning that fraction into a negative exponent. And this is technically going to be the limit as, say, t gets big of the definite integral between 6 and t of x cubed to the minus 3 dx. And that's going to wind up being the limit as t gets big. Let's see, that's not quite readable, so let's make that a bit more readable. As t gets big, let's see, when I integrate, I'm going to get x to the minus 2 over minus 2, and I need to evaluate between 6 and t. And so this first integral is going to be the limit as t gets big of, let's see, we're going to have t to the minus 2 over minus 2 minus 6 to the minus 2 over minus 2. And let's clean this up. We'll deal with the limit at the end of this. I want to go back and deal with these negative exponents. We're actually going to have 1 over minus 2t squared, and then we're going to have a minus 1 over 2 times 6 squared. And so when we look at this, we're now looking at the limit as t gets big of, we have 1 over minus 2t squared plus, let's see, 1 over 2 times 6 squared, that's, let's see, 2 times 6 squared is, let's do this in some scratch work, that's 2 times 36, and 2 times 36 is going to be 72. So we have plus a 1 over 72. And as t gets big, this fraction goes to 0, and as a consequence, our limit becomes 1 over 72. So this particular side of our inequality is 1 over 72. Okay, well, what about the other particular improper integral? Well, let's go looking at how we find it. So the improper integral between 5 and infinity of x to the minus 3 dx, that's going to be the limit as t gets big. It's exactly the same kind of problem. Of the integral between 5 and t of x to the minus 3 dx. And so we're still going to have the limit as t gets big of x to the minus 2 over minus 2. Evaluate that between 5 and t. And when we do that, we're still going to have the limit as t gets big. And this time we have t to the minus 2 over minus 2 minus a minus 5 to the negative 2 over 2. I've basically dealt with this minus sign here on the second part becoming that plus sign. If you track it through, you'll see that that's what it winds up being. And then when we clean this up in the algebra, this is going to be the limit as t gets big of 1 over minus 2t squared plus 1 over 2 times 5 squared. And again, as t gets big, this fraction is going to go to 0. And so when we pass to the limit, we wind up getting 1 over 2 times 25, or 1 over 50. Now, what that means is, in going back, this side is 1 over 50. And I want to stare at this for just a minute, and I kind of want to highlight what we're going to be looking at. What we now have is that 1 over 72 is smaller than our tail, and our tail is smaller than 1 over 50. And I need to remember that for getting to the next part of the solution. So we come to the next blank page, and we're going to remember that what we've got is 1 over 72 is smaller than the tail if we chop it at S5, and the tail is smaller than 1 over 50. So what this says is that the infinite series itself let's see, let's recall that the infinite series itself is S5 plus R5. And so what we have is S5 plus R5 is going to be smaller than S5 plus 1 over 50, and it's going to be bigger than S5 plus 1 over 72. And so what we now have, and remember that, let's put this in a different color, that S5 wound up being 1 plus 1/8 plus 1/27 plus 1/64 plus 1/125. That's what S5 was. And when I put that back in, what I wind up getting is that 1 plus an eighth plus a 127 plus 1 over 64 plus 1 over 125 plus 1 over 72 is less than the series that we are trying to bound between two numbers. And that series is less than S5, which is again 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125 plus 150. Now, if I want to get decimals, that again is something for calculators or Mathematica, so let's go into Mathematica. And so all we're going to be doing, I want decimals, so I'm going to be hanging a capital N around two things. We'll look at capital N of that series 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125. And then, of course, I also want to add 1 over 72. And I want the decimal equivalent of that number. Let's pull this out just a little bit. So the decimal equivalent of that number is 1.19955. And then for the upper bound, I'm going to look at that same basic idea. The only thing is that the upper bound has a 150 at the end of it. And so you'll notice that it actually is bigger. Now we've got to remember those two numbers. So let's see. The small, and I'm probably going to have to come back. So the smaller number is 1.19955. So if I come back here, I have 1.9955 is less than my series. Actually, let's clean this up just a little. $1.9955 is less than my P series. And we're going to go back to Mathematica. And, I messed that up. It's a 1.199. So let's come back here and clean that up. So this should be 1.199. And this guy is less than 1.2 something or other. So let's go back to Mathematica and find out what that upper bound was. And the upper bound is 1.20566. So 20566. 20566. So this particular infinite series is trapped between these two numbers. Obviously, this is the upper bound. And this is the lower bound. Now, I want to look at a second question dealing with p-series. So let's look at a second question of the same, of dealing with tails. So my second question is going to be this. How many terms do we need to add to get an estimate for, let's stick with the same p-series. So we're looking at the series 1 over k cubed as k goes from 1 out to infinity. And I want to have an estimate for that particular series that is accurate to, say, 3 decimal places. Well, the way that we're going to look at this particular problem is we're only going to worry about the upper bound. The upper bound gives me an idea of how much error I might have. And so what I want to be thinking in terms of is that the series itself can be thought of as Sn plus Rn, and Rn is known to be smaller than the integral between n and infinity of 1 over x to the p, well, in this case, 1 over x cubed, dx. And so I need to find an n such that this integral is smaller than 0.0005, because for 3 decimal places worth of accuracy, I need the error to be smaller than 5 times 10 to the minus 4th. Well, the next step here is going to be finding that integral. So we now look at evaluating that integral. So the integral between n and infinity of x to the minus 3 dx, that looks just like the previous ones that we've done. We set it up as a limit as t goes to infinity from n to t of x to the minus 3 dx, and we're still going to get the limit as t goes to infinity of x to the minus 2 over minus 2 evaluated between n and t, and this time the limit is going to look very similar to the previous ones. It will look like a 1 over minus 2 times t squared minus a minus 1 over 2n squared. Now as we take the limit as t gets big, we want to notice that this fraction goes to 0. So when we pass to the limit, we wind up getting a limit of 1 over 2 times n squared. Now, since we want to have our estimate accurate to 3 decimal places, what we really want is we want to make this bound smaller than 0.0005, because if this bound is smaller than 0.0005, the actual error, which is smaller than this number, will also be less than 0.005. So what we want to do next is we want to make a table of values for 1 over 2 to the n squared, and we simply then look for the first n that makes this guy small enough, which in our case is 0.0005. Now that's a job for a calculator or Mathematica, so we're going to go back to Mathematica. So what I'm going to do is I'm going to make a table And the table is going to be in comma. Let's see, I'm going to go ahead and look at decimal values of 1 over 2 times n squared. And I want to look at that. Oh, let's look at the first 10 of them. And when I do that, I notice that even with n is equal to 10, the bound on the tail of the integral is still way too big. So I'm going to have to increase my table. We'll go from 10 to 50. And this time, when I look at the integral values, I notice that by the time I'm at 50, I'm way smaller than the bound that I need to be, which is 0.0005. So we back up and we start looking, and we start realizing that, 31, the integral is still just a little bit too big. It's 0.0005. But at 32, the integral is small enough. The integral is now 0.0004. So at 32, when n is equal to 32, we should have enough accuracy. So what does this actually say? Well, this says that 1 over 2 times 32 squared is smaller than 0.0005. And so that says that if we look at S32, that should be accurate to 3 decimal places as an estimate for the entire p-series. In other words, what I want to basically be thinking about is that if I round S32 and I round the p-series itself to 3 decimals, they should be the same thing. So what I want to do now is, let's see, S32 is the sum, as k goes from 1 to 32, of 1 over k cubed. This should be a good enough estimate. That should give me 3 decimal places worth of accuracy. Now, if I actually want to look at that particular value, if I want to look at my estimate, that again is a job for a calculator or Mathematica. So to look at the actual estimate, what we do is we feed it to Mathematica. So we're going to actually go back to Mathematica and see what that estimate is. So I want to look at the sum. I don't want to do it there. I want to look at the sum of 1 over k cubed as k goes from 1 to 32. And Mathematica gives us this ugly, horrible looking fraction, which of course is useless to us, so we will change that into a decimal with the capital N command. And that's much better. The actual S32 is going to be 1.20158. So let's get that written down in our notebook. So S32 is 1.20158. And just to make sure, let's go back to the Mathematica. And yeah, this number here agrees with what I wrote down. So that's S32. And if I round this to 3 decimals, I get that S32 is approximately 1.20. Well, that's a bigger than a 5, so it's going to round to 1.202. And the series, well, I still don't know what it converges to. If I round the series to 3 decimals, the series will also be 1.202.